Setting up the grid using variables. It helps for any later scans to set variables for what we might later change. The constants are for variables that are defined by numbers, while the parameters are dependent, defined in terms of constants and other parameters. The first two variables we will add are the beginning and ending values of x in the simulation. We can see some guesses by looking at the grid parameters. Having done that, we define the constants. Begin x equals minus 0.11 and end x equals 0.19. Then we go down to the grid, and in the grid, using right-click on the variable, we can assign the value to be the variable that we've assigned in both cases, beginning and end. Since the waveguide will be powered at the maximum of x, we choose the maximum of x so that the waveguide extends just outside. However, the minimum is closed off, so we choose the minimum of x so that the lower x end of the waveguide is inside the box by some margin. Next, we add the beginning and ending values of y. We set begin y to be minus 0.101 and end y to be plus 0.11. And we proceed through getting all the values, setting it in the grid, using again right-click for each of the grid values. And then having done that, we can see that we've chosen it so that the tube just exits the simulation on both ends, and the waveguide exits the simulation, but that other than that, the cavity is contained inside. Now, from those parameters that we've defined, we can compute the length of the simulation box. So we define the length in x as being end x minus end y, and we define the length in y similarly. And finally, the length in C. And now we know the lengths of everything in this, of the cavity in the simulation. Now next we define a constant called resolution, which will be interpreted as being the number of grid cells across one of the cavity cells. For start, we set that to 20. Now from the minus z view, we can see, going to the minus z view, we can see that cell covers about 3/4 of the grid length in y. So we define an estimated desired cell size to be DLS to be 0.75 times the length of y over the resolution, so that resolution can be interpreted as approximately the number of cells across the widest part, the equator of the cavity. From this estimated cell size, we can compute the desired number, cells x, of cells in the x direction. That's, we can see, is 30. And similarly, we can compute cells y and cells z. Now, in order to get these things right, we actually have to take that division and take the rint, the rounded integer value for each of those, to make sure that we get an integer number. And now we put these numbers into the grid using right-click substitution. We can now turn to adjusting the grid resolution. The grid resolution is set such that the important features are resolved. Now for this, we will look at the HOM couplers using the -Z view, which shows the details of the HOM couplers. We can see that we are not resolving these well. We probably need 3 times as many cells. So let's set resolution to 60. This multiplies out to about 4 million cells, but we can now see that we're just now resolving the HOM couplers. With a reasonable grid, we can now look at the tessellation, which is the deviation of the tessellated surface from the actual surface. Before doing that, we will save this simulation as the next one in the sequence. At this point, we've finished most of setting up the grid, and we will move on and restart with checking the grid resolution.